Welcome, everyone. We have a really fascinating stack of sources for you today. It starts with some pretty visceral fictional horror, the new series Alien Earth. But then it spirals out into, well, some of the deepest questions you can ask about astrobiology, philosophy, and the whole search for life beyond Earth.
That's exactly right. We've synthesized a whole range of material here, everything from detailed creature analyses like the new xenomorph taxonomy, all the way through NASA technical reports, some going back decades, on finding life on Mars.
Yeah, and even philosophical essays on, like, the Fermi paradox and cosmic silence.
Right. So the mission for this deep dive is really to use the, let's say, intricate biological details you find in science fiction as a kind of springboard.
A framework.
Yeah, a framework to analyze the real science. Things like xenobiology, the actual challenges of detecting life, say, on Mars, and then thinking about the bigger implications of, well, silence out there.
We've pulled together some really surprising facts for you here. I mean, stuff like fluoropolymer armor plating on aliens.
Right.
To a pretty wild philosophical theory about why advanced aliens might just choose to be quiet. So let's just jump right in, starting with our new fictional monsters.
Let's do it.
Okay, so Alien Earth is out. And the general feeling we pick up from the reviews is that the creators, they actually managed to avoid that, common trap.
Which one? Splitting the movie idea thin.
Exactly. Splitting a 2-hour movie concept into like an 8-episode behemoth. Apparently the pacing really works, and it delivers some intense horror.
It seems to, yeah. And the central human story sounds pretty complex, too. It's focused on this character, Wendy. She's a child, but she was put into an adult synthetic body to, save her life.
Right. So she's dealing with this accelerated maturity, trying to grow up way too fast while, fighting literal monsters.
And that's where those Peter Pan references come in, apparently, around her group of young survivors, the Lost Boys.
Yeah, and they're being hunted by this calculating CEO antagonist Boy Cavalier. It's all quite layered. But the creature that really grabbed everyone, and probably cost me some sleep, is something totally new. It's got this horrific name, Trypanohyncha.
Which everyone is immediately calling the lovable little eyeball octopus parasite.
I have no idea where the lovable part comes from. Seriously.
Yeah, that thing sounds like pure nightmare fuel. Its behavior is just gruesome. It attacks the host, surgically removes an eyeball, and then uses those pathways to connect directly into the brain. Basically takes over the host's body completely.
And it has that defense mechanism too, right? The toxin.
Yeah, releases an airborne toxin if the host or anyone else tries to remove it. Just nasty.
So, okay. Let's pivot a bit.
Yeah.
Let's take these fictional monsters
and
kind of run them through the filter of actual science. Xenobiology.
Right.
And it feels like you almost like to start with the classic xenomorph, right?
Right.
Did the sources we looked at actually try to give that original creature like a formal scientific classification?
Oh, absolutely. They went for it. The proposed designation was Xenomorphus extraterrestris, falling under a new order, Xenomorpha and family, Xenomorphidae. But morphologically, based on its structure, the sources were able to place it. It fits within the phylum Arthropoda.
Arthropoda, like insects and spiders.
Exactly. Because of the segmented body, the rigid exoskeleton, and that scorpion-like telson or tail, specifically they placed it in the class Chelicerata.
Chelicerata. Okay, so we're basically talking about something structurally related to spiders and scorpions. 8 legs, segmented body, grasping bits.
That's the idea. It grounds the design, in a structure we can recognize from Earth biology. It helps picture it.
Okay, so what about the really famous part, the blood, the acid blood? Its hemolymph is notoriously corrosive. How does a creature even contain acid strong enough to melt steel without dissolving itself?
That is the million-dollar question, isn't it?
Yeah.
The sources hypothesize that the corrosiveness comes from specific organic acids, things like thioacids and haloacids, probably generated by a really unique metabolism.
Okay, but how does it contain it?
Right. So to combat that, the theory is that the xenomorph's exoskeleton contains molecular inhibitors and anti-corrosive substances, specifically fluoropolymers.
Fluoropolymers,
Like the class of chemicals that gives us polytetrafluoroethylene, PTFE.
Wait, you're telling me the xenomorph is basically wearing a suit of Teflon armor?
Huh. That's the hypothesis, yeah. Pretty fantastic, isn't it?
That explains so much about its resilience, even after it's dead.
It really does. And its energy source. That's maybe even more critical to its survival. It's thought to use a stream of electrons.
Electrons? How?
Powering itself in a way similar to some organisms here on Earth, chemolithotropes. They literally get energy by oxidizing inorganic compounds.
So it doesn't need like a normal food chain. It just needs a source of electrical potential. or chemical potential.
Pretty much. That's what makes the xenomorph truly cosmically tenacious, as one source put it. It could potentially exist almost anywhere.
Wow. Okay. Now let's swing back to that the new eyeball parasite thing that Tia
A most lovable one.
Yeah. Is the idea of this super intelligent tentacled brain taker.
Yeah.
Is any part of that plausible?
Well, some elements are more plausible than others. It's high mobility and intelligence. Maybe?
How so?
You could maybe argue for something like distributed ganglia, similar to what real octopuses have. That allows for complex, coordinated actions without, a single dominant central brain controlling everything.
Okay, so distributed intelligence is a thing.
But yeah, the really implausible bits, the extreme length of its tentacles seems biologically costly. And maybe the biggest question is why? Why would an organism that seems so formidable on its own need to be parasitic at all? That kind of pushes the boundaries of evolutionary logic.
Yeah, that's a good point. Speaking scientifically, is that evolutionary cost developing this incredibly complex, brain-hijacking, parasitic method, is that actually justified? It seems like overkill.
It does seem like overkill. That's probably the least plausible part from a strict evolutionary standpoint.
Still, these fictional monsters, they're often defined by that parasitoid behavior, aren't they?
Yeah.
Using a host as an incubator or a puppet. Do we have real-world parallels for that kind of horror?
Oh, absolutely. Nature is full of this stuff. The xenomorph's facehugger and chestburster stages, classic parasitoid strategy.
Like what?
Think of parasitic wasps, like Glyptopantelles or Megarhissa. They lay eggs in a host, the larvae eat it from the inside out.
Right.
And the newer neomorphs from the prequels, the ones with a fungal element, they're very similar to parasitic fungi like Ophiocordyceps.
The zombie ant fungus?
That's the one. It seizes control of an insect's nervous system, forces it to climb to a specific spot where the fungus can erupt and spread its spores. Horrifyingly real.
And so the sci-fi horror trope is actually just mimicking terrifying jungle reality.
Doesn't it look yeah, that's genuinely unsettling.
It is. And that connection, it kind of brings us from this expertly designed fictional biology right into the real hunt for life. If we're actually looking for life out there, whether it eats electrons or is just simple microbes, where do we even begin? I guess we have to start with Mars, right? Our neighbor.
Mars is definitely the closest potentially viable target. You have to grasp just how brutally hostile that environment is. The atmosphere is incredibly thin, mostly CO2.
Right.
And the surface pressure is tiny, only about 1/100th of Earth's.
And that low pressure is the real killer for life as we know it.
It's the critical limiting factor, yeah. Because liquid water, the absolute foundation for life as we understand it, it just can't exist stably on the surface. It boils away, vaporizes almost instantly.
And then there are the temperature swings. Wild, right?
Just extreme. You're dealing with severe diurnal cycling. It can swing from maybe a comfortable 30 degrees Celsius near the equator during the day
Okay, not bad.
down to a deep freeze of minus 70 Celsius at night. Plus, there's high surface radiation because Mars lacks a global magnetic field. It's a tough place. Maybe life is protected underground, but the surface is harsh.
It's really interesting, though, looking back at how scientists planned to tackle that hostility decades ago. We pulled this old NASA report from 1965 about the strategy for the very first Mars landing mission.
Oh, yeah. What did they prioritize?
They were incredibly methodical. They stated that any life detection experiment must focus on what they call the three fundamental attributes of life: metabolism, reproduction, and macromolecules, organic compounds.
Makes sense. The basics.
And they seemed most interested in metabolism, first looking for energy consumption. Why that specific focus back then?
Well, metabolism was seen as the most promising attribute because it's essentially continuous, right? It's an ongoing process, something that should be detectable.
So you don't have to catch a cell in the act of dividing.
Exactly. You just need to measure the subtle changes it causes in its environment. Things like heat production, maybe changes in the gas composition of the soil, or shifts in pH. It's about detecting the process of life, not necessarily the living thing itself directly.
Smart. And what were their other priorities for those initial landings way back then?
High priority also went to chemical studies. Analyzing the soil, looking for carbon, organic materials, specific ions that we know are associated with life here on Earth.
And landing sites. Did they have ideas?
They did. They favored landing sites like Syrtis Major, one of the big, dark areas in the southern hemisphere. That was based on early telescope observations suggesting seasonal darkening.
Which they thought might be.
At the time, some speculated it could be due to the proliferation or growth of Martian organisms like vegetation, responding to seasons. We know better now, of course, it's mostly dust shifting.
Fascinating glimpse into past thinking. But today, the search has really broadened out, hasn't it? Beyond Mars, into the outer solar system. That's where things get maybe even more exciting.
Absolutely. Current high-priority targets are really the icy moons. Europa around Jupiter and Titan and Enceladus around Saturn.
Because of the oceans.
Exactly. They're compelling because they seem to harbor these potentially huge subsurface oceans hidden beneath thick shells of ice. That offers stable conditions, protection from radiation, possibly lasting for billions of years.
So how do we even look for life there under all that ice?
Well, the technological focus now is shifting towards developing what people sometimes call tricorder technologies, basically advanced instruments designed for in situ analysis.
Like analyzing stuff right there on the spot.
Precisely. Things like nanopore sequencing systems for single molecule detection. The goal is to analyze complex biomolecules right there where we find them, on Europa or Enceladus, rather than having to bring samples all the way back to Earth.
Okay, so we've covered the potential for life, the science of looking for it, the sheer ingenuity needed to detect it. Now let's tackle the big looming challenge, the silence. If life is so tenacious, if xenomorphs can theoretically eat electrons and there might be vast oceans on Europa, why does the cosmos seem so quiet?
Yeah.
That question plunges us right into the philosophy of the Great Filter, doesn't it?
It really does. It's the heart of the Fermi paradox. If the universe is so vast and old, where is everybody?
And the Drake equation is usually the starting point for thinking about that.
Right. Formulated by Frank Drake back in 1961, it's basically a way to estimate the number of communicable civilizations in our galaxy.
It looks like a simple probability argument on the surface, but what's really clever is how it forces you to combine variables from completely different fields, right?
Exactly. That's its power. It makes you integrate astrophysics star formation rates, planets per star, with planetology, habitable zones, with biology, the chance of life arising, intelligence, and then that really tricky variable, L, the lifetime of a technological civilization.
And when you plug in even halfway reasonable, maybe even conservative estimates.
The simple math often spits out a final number, and the number of civilizations that's, well, depressingly close to zero, or at least far fewer than you'd intuitively expect. And that's the paradox. Where are they?
Which leads us to some really mind-bending proposed solutions, including one we found called the Kantian-Wantian solution. Sounds very philosophical.
It is deeply philosophical. It hinges on a concept called normative non-naturalism.
Okay, break that down for us.
Okay, put simply, imagine discovering a universal law of ethics that's as fundamental to the cosmos as, say, gravity is to physics.
A universal moral code.
Kind of. It's the philosophical belief that objective, universal, mind-independent moral facts exist. And crucially, these moral facts are not reducible to the natural, physical facts that science usually deals with. There's something else, something non-natural.
Wow, okay, that's a massive claim in itself. How does that solve the Fermi paradox?
Well, the hypothesis suggests that any civilization that advances far enough technologically enough to achieve interstellar travel and galactic colonization inevitably discovers these universal moral values as part of their intellectual maturation.
And finding these values changes them.
Profoundly, yes. The idea is that this discovery transforms their motivations. They develop what the source calls a quietist desire, a preference to simply contemplate the universe, to understand it, rather than imposing their will on it or expanding aggressively. And that, supposedly, explains the Great Silence. They're out there, but they choose to be quiet observers.
Hold on. So you're saying that every advanced civilization, regardless of how utterly alien its biology or evolutionary path might be, whether they evolved from, I don't know, electron eaters like hypothetical xenomorphs or eyeball parasites, they all independently discover the exact same moral code.
That's the implication of this specific hypothesis, yeah.
Yeah. Doesn't that feel, well, incredibly anthropocentric?
Mm-hmm.
It seems to assume a universal morality based on maybe our own limited ideas, and it kind of rules out the possibility of truly alien ethics, maybe ethics we couldn't even begin to comprehend.
That's a very strong critique, yes. It is arguably an anthropocentric hypothesis about morality, projecting a specific, perhaps human-derived ideal onto the cosmos. But it does offer a rather hopeful, if speculative, answer to the paradox, suggesting that technological maturity inherently leads to wisdom and quietude.
But that quietude, that choice to prioritize contemplation over colonization,
Yeah.
it sort of mirrors a debate we have right here on Earth, doesn't it? It's
Yeah.
about the value of space exploration versus focusing only on problems here.
It absolutely does. And that brings us neatly back to another bias identified in the sources, ground bias.
Right. Explain that one.
Ground bias is defined as this kind of generalized hostility or maybe just skepticism towards the value of human activities in space. It often comes from this tendency to prioritize only Earth-centric concerns.
Like seeing space budgets as just taking money away from fixing things here, like tax issues or poverty or climate change.
Exactly. It's viewing space as a distraction, an expensive luxury. It's a limitation based on, familiar immediate ways of thinking. It's a form of anthropocentrism, focusing only on the ground beneath our feet.
But the counter-argument is that exploration isn't really separate from our concerns here at all, is it?
Precisely. That's the key point. Understanding our own planet often relies heavily, sometimes directly, on space science.
Like the Venus example.
Perfect example. The early research into Venus's atmosphere, discovering that runaway greenhouse effect, that had a huge impact on shaping our understanding of climate change models right here on Earth. And it helped advance our knowledge of the ozone layer back in the 60s and 70s.
So ground bias is basically short-sighted.
You could argue that, yeah. It potentially undermines the long-term scientific and even ethical value of exploration because it creates this false separation between out there and down here. Our understanding of Earth is deeply connected to understanding the solar system and the universe around us.
Wow. So we've really gone on quite a journey here. From dissecting fictional biology.
Teflon-armored aliens and eyeball parasites.
Right. Through the very real, meticulous science of trying to find life on other planets, all the way to these really profound philosophical questions about existence and silence.
Mm-hmm.
It seems like whether we're designing fictional xenomorphs or debating the quietude of hypothetical galactic civilizations, the whole effort to finding life, detecting it, engaging with the idea of it, it fundamentally challenges how we see ourselves, doesn't it? Our place in things, and even what life really is.
It absolutely does. And perhaps here's a final provocative thought for you, something to mull over. Drawing from the philosopher of science, Michael Crow. He pointed out a really common methodological fallacy in the search for life. We often mistake necessary conditions for sufficient conditions.
Meaning?
Well, take liquid water. It seems absolutely necessary for life as we know it. But just finding liquid water on another planet doesn't automatically mean that planet is sufficiently equipped to be inhabited. Finding the ingredients doesn't guarantee the cake, right?
Right, okay. There could be other necessary conditions we don't even know about yet.
Exactly. And the sheer difficulty of proving a planet is truly inhabited, not just habitable, but actually inhabited, means we probably won't know the complete set of necessary conditions until we actually find that first definitive sample of extraterrestrial life.
If we ever do.
If we ever do. So until then, how long do we keep searching? How long do we keep refining our methods, our theories, our very concepts of what life could be, knowing all the while that the existence of life somewhere else is, in principle, verifiable? We could find it. But the non-existence of life, that's something we can likely never empirically falsify across the entire cosmos. How long do you search for something you can prove exists but can never prove doesn't?